in this meeting now, we want to talk about disruptive manufacturing. And one of the key things I want to try and get across is that if we look at manufacturing, as we just heard from Paul, that the new things that are happening in manufacturing will take place if we look at manufacturing in a slightly broader way. Because if you look at the Latin definition of the word manufacturing, it means by hand. But what we're seeing in a broader context is that if you begin with this exciting field of ideation, 3D printing, and make that part of manufacturing as a front end, and then as Paul was hinting at, bring the service aspects of a product in, then you have a much broader concept of a pipeline. So actually, whenever I'm doing this, I often invite people to look at the back of their iPhone, because most of the iPhones say, designed by Apple in Cupertino, assembled in China. Mine says that, and that's kind of a nice way of thinking about manufacturing as a much broader topic than that cute video that Paul showed with the hammer and the gentleman who was very befuddled by it. This lab is something that I built 3 years ago. We had done a number of 3D printing projects at Berkeley, and they were also stuck in the research field. And I actually wanted to do something different in my classes rather than be the professor at the front of a stage. I'd now actually have all of these students sitting at tables, and we give out the products, electronics. We have 3D printing machines all around the room. And basically for their class, they begin some design work at the beginning of the semester. They think about a product halfway through that they're going to make in groups. And this ideation lab is turning out as a fabulous way of getting people much more interested in manufacturing than ever before. Classes that we have running in labs like this now at Berkeley are really a nice combination of computer scientists, electrical engineers, mechanical engineers. And so if I had to say one thing in this meeting that makes manufacturing different for me, it's the front-end ideation, which is really exciting a large number of our students and has changed the way things are being done. Connecting that to research, I deliberately did this cartoon for this meeting, cartoon-like in order to sort of get your attention a little bit, where what we're also seeing is that for these next generation products, like the Apple iPhone is a good example, we want to get people early on, rather like Paul just said, early on to come up with new ideas, mix them together so you can have a chip designer, a packaging designer, a peer review, and a prototype designer all going on at the same time. And in the bottom right-hand corner, I did a sketch of a sort of older-looking manufacturing person because we want to get them in the loop as well. So in this final slide of mine, you have to look at this in real time. This is a design that's being done in a lab, and it's being sent over the internet to a molding company. And the idea here is that the person who's the designer says, I'd like to set up a mold to cast this model in bronze. How should I go about it? But immediately, that person is getting real-time feedback from the molding house, which might be many time zones away, discussing some of the more difficult parts of the device. And so as the end of the product there, what happens about the next part of if I'd have continued this, the designer is told by the manufacturing people that can be made, but it has to be split into 4 different components. There has to be 4 separate molds, and so you can go ahead provided you make this particular change. So the goal is, what I thought about this project a long time ago was that I wanted to have a silver-haired machinist looking over the shoulder of a younger designer, trying to give them pop-ups and advice about how to get that going. Even in my class, I really emphasize very quickly, even though I'm teaching them about 3D printing, just simply put, it would be a disaster if they leave the class thinking that 3D printing gives you the device, because eventually it's going to go to a molding house and you think about draft angles, shrinkage, will the mold fill, and will the printed circuit board fit in there? So this interactive design that I tried to capitalize on that previous slide, I think is really key to manufacturing and the front end to manufacturing. So with that in mind, I think the first thing I can do is hand over to Jason, because with his really exciting technology around 3D printing, I think he can describe some really interesting new techniques there with very many new different kinds of product opportunities. But I think you'll agree, right, that there's some advantages to traditional manufacturing, but you have to be careful and wily about how it's going to be rolled out in volume. Is that a nice tee up for your talk?
Sure, that's terrific. Yeah, it's a pleasure to be here. And what I'd like to talk about today is obviously in 3D printing, but I'd like to start with the question of why isn't 3D printing used in manufacturing? And I think immediately two answers pop up. One is print speeds are incredibly slow. Not unusual to see print speeds in 3D printing on the order of 5 to 10 millimeters an hour at the fastest. The second, and perhaps an even bigger problem, is the materials just simply don't lend themselves to manufacturing. They don't lend themselves to even functional prototypes, never mind final product form. And so at Carbon3D, we're commercializing a technology we call CLIP. What you see here is a printer that is printing this object. It's projecting light similar to other 3D printers, but what it's doing differently is it's printing this object continuously. And this video is sped up for this presentation, but the real-time print speed of this is 200 millimeters an hour. And the way we're able to do this is we harness the reactive power of oxygen in order to print continuously from liquid materials that solidify when exposed to light. Another big issue that we believe is solved by CLIP is we're able to print with new material, high-performance elastomers. And so the unique features of CLIP have allowed us to create many different categories of materials that are useful to designers. Elastomers are very difficult for any 3D printing technology, and we've been able to unlock chemistry that allows one to do that. I have samples at my desk if people would like to see them. So in closing, Carbon3D, we exist to enable designers and manufacturers and creators like yourselves to create the products of the future, starting with the functional prototype, but eventually paving the way to 3D manufacturing and being able to open up and free creators from the design constraints of generating products.
That's a great summary. Thank you. Thank you very much, Jason. Let me switch now to Robert, who also has been prototyping new products in the space of microfluidic systems, biomimetic camouflage and display, and in the same kind of space as Jason. Robert, maybe you can expand on some of your prototyping work and markets for it.
So I'm actually a consumer of machines like the ones Jason is making and adapting them for new things. If you think about the assembly of transducers into complex machines like actuators and sensors, you can start with basically soups of liquid that do interesting things, like that are electrically conductive, allow capacitive sensing, and allow forceful actuation and electrical displays. And you can use existing manufacturing systems like injection molding, rotational casting, and even 3D printing. So this display on the left is the most extensible display in existence using electrically powered light emission. It's a linear strain of 500%. The next best system that I'm aware of goes to 200%, is an OLED-based system. Made very cheaply, very quickly. It's obviously a low-resolution, 1 pixel centimeter square area display, but we actually have now scaled it up to millimeters squared over 10 square inches. The yellow tentacle-like thing was 3D printed on a system similar to what Jason talked about, but much slower because we don't have Carbon3D's substrate capabilities, and I assure you will be the first people to buy it academically when it's available. The heart that you can see is an injection molded silicone foam that pressurizes 2 internal chambers and actually pumps liquid. We intended it just as a demonstration, but it turns out that medical doctors really do believe it's useful for non-invasive or less invasive ventricular assist devices. And the video on the right show you an orthotic that we rotationally cast, a feedback-controlled orthotic that allows assistive manipulation of delicate objects, as well as allowing people with reduced musculature to apply greater forces and assisting in the rehabilitation of those with stroke patients. The bottom left video of the square shows a feedback-controlled haptic interface with a soft skin that operates a lot like your skin on your hand, feeling touch, and then it displays that back pneumatically. All of these using existing manufacturing methods, very rapid. And I'd like to point out, continuing the theme of talking about Toyota, that their vision is one-piece workflow. And these methods are all intended to get towards that ideal. And if Jason's technology, with Jason's technology, I think you can actually get to that ideal.
Good. That's a great start. And Rob, we'll come back to both of you in a second. Now, with Jim next to me, the thing to really begin to stress, though, is how do these very exciting technologies that you've seen in these videos producing one or two components at the beginning, and Jason said it's slow, and you don't always get a product out which is mechanically viable. Eventually, all of these exciting new technologies that you've seen need to be scaled up in factory situations. And I think that's where Jim, next to me, has the experience of doing that kind of work. And I'd like to hand over to him to look at the big production volume aspect of these exciting new technologies.
Thanks, Paul. So I'll move us from micro to macro. I have UCLA by my name, but I'm actually here as a result of the SMLC in the upper left-hand corner. That's the Smart Manufacturing Leadership Coalition. I'm the CTO of that organization, which is 50 companies and institutions that is implementing smart manufacturing. So you're going to find that my remarks are very, very similar to Paul. Paul, you actually set me up in about as good a way as one could be. The Brilliant Factory and GE is actually part of our group, and we've been influenced and rolled a number of things from that kind of thinking into what we're doing. But I have only 2 minutes, and so let me explain this. So smart manufacturing, a term we coined about 10 years ago, is the act of making data a key asset. So very similar to what Paul is saying. And it is about taking it as a key asset and shifting the business focus from facilities to virtual enterprises. Again, the same point. It is really about addressing global competitiveness and new product demands, but doing so with enterprise responsiveness, making energy productivity and environmental sustainability competitive advantages, and it's about radically higher productivity, getting at those bubbles that Paul was talking about. Of course, market and technology agility are important. It is about getting at sub-optimization, where there are seams and transactions, as we call them, as a result of compartmentalization, and it is about going after untapped opportunity with enterprise optimization. The one thing I would add to what Paul was saying is, to us, smart manufacturing is about unprecedented real-time data and modeling capabilities that are applied through modern cloud technologies. We'll say a bit more about that has already transformed other economic sectors. So we're bringing cloud in a functional way to manufacturing. So I'd like to just explain smart manufacturing with a few simple examples that from our coalition. And if you just kind of think about the chart from right to left, one of them is General Mills in Minneapolis is shifting from air-prone product forecasting to customer demand-driven production, and it is reducing its inventories, which increase, by reducing it, you reduce the probability of contamination. Praxair in Port Arthur, Texas is using image sensors and high-fidelity modeling so that they can see and shape energy distribution inside a steam methane reformer, saving many % of energy, and they'd like to do this in 12 other plants across the U.S. We have a large aerospace company that would like to brand its product as environmentally sustainable. We have a wine company that would like to brand its product based on chain of custody. General Dynamics in Scranton, Pennsylvania is dynamically configuring heat treatment furnaces to improve metallurgical properties so they can reduce defects and reduce machining and reduce electric costs in the machining downstream processes. And we have a region of small companies in California that like to save electricity costs but work as a collective with the utility so that the utility can manage peak load and bring renewables into the grid in a better way. So these are all examples, but if we go back to the main point, same point that Paul was making, data is an asset. Modern cloud technologies as industry infrastructure, from our perspective, make it possible to change the paradigm, to take data from application, take the application instead of taking the application to the data. It is a paradigm that changes the business model, and it cuts cost and time to deploy systems in half. And then from our perspective, smart manufacturing is the business vertical of Internet of Things. And as I said, the SMLC is a coalition that has come together to implement industry-wide infrastructure to tackle this problem.